Okay, everybody. Just following up from last lesson, we talked about bearings and sit down, please. I'm trying to start the lesson. That may be so, but there's a time and place. Yes. Sorry. Thank you. So we talked about angles of elevation and depression, and we finally talked about bearings. Just to remind you of the scenario that was given out, a pirate ship leaving port P gets to port X after a couple of direction shifts, so boom, boom, like so. And we use right-angle trigonometry to figure out the direct distance, or the as the crow flies distance between the port and where X marks the spot. So it's labelled D here. And we did it by arranging it into a series of right-angled triangles, with the final result being 20.7 kilometres away from the port. Okay, so we're going to revisit this, except we're going to utilise something which you are familiar with, I know, because I think it's general maths, or just maths methods, but either way, we're going to look at it again. So from the previous lesson, here is the triangle reproduced again, point P to point X. So we're looking for the distance D, and we know what we have is two sides that we do know, a side that we don't know, and we have an angle opposite the unknown side, 80 degrees. What we can say with absolute certainty is that we cannot use Pythagoras' theorem directly in order to solve this problem. You just can't, because Pythagoras' theorem is a result that eventuates from a right-angled triangle. Now, I'm not going to prove why this is so, but what I am going to say is that, just to give you a little bit of an insight, that if I take this corner here, X, and drop, actually I'll just use a different colour, and drop a line down here so it's perpendicular, like so, we have effectively split that triangle into two right-angled triangles. Now if you can imagine, because I've got two right-angled triangles and I have an angle here and I have some sides here, I can effectively use Pythagoras' theorem by a couple of different routes in order to calculate it. Now, this idea is transferable across all triangles, not just right-angled triangles. So if we have a result that we can repeat over and over and over again, what we do as a mathematician is we create a rule. So that instead of doing it from what we call first principles every single time, we just simply refer to the rule and utilise that. Okay, so this is called the cosine rule, and what I'm going to do is I'm going to demonstrate or show you the cosine rule, and on Google Classroom at 3 o'clock a video will be posted. It's a 4-minute video, and it will show you how the cosine rule is constructed using that idea of splitting a triangle into two right-angled triangles. As always, I'm a big proponent of constructing meaning for rules so that you are more likely to utilise them effectively. But I'm not going to force anyone to watch the video, but if you've got 4 minutes of your life, then it's well worth a quick look so you can make sense of this rule. So right now, all I'm going to do is I'm going to show you kind of what the rule looks like. This might be different from how you've done it before. I will give you algebraic rules, and what I find though is that people rely too much on the letters, and then if the letters happen to be in a different spot, they still follow the letters and then they get the wrong result and they don't get why. So in my first pass through the cosine rule, I'm simply going to describe it in terms of position rather than letters. So the cosine rule is utilised to either find a missing side. A missing side, assuming that you've got the other two sides plus the angle opposite that missing side. Okay? You've either got it directly in the diagram or you're given enough information in the question to figure these bits out. So you can see I call this leg 1 and leg 2. And it's because an angle is always made up of, it's called subtend, but it's made up of two legs, right? So you've got an angle between two legs. And so in terms of the triangle, what you're looking for is, do I have the two legs and an angle in between? And am I trying to find the opposite side? Okay? That's the picture you need to be looking for. Okay? An angle, an opposite unknown side, and two legs. Okay? So you've got, I'll just do it in a different colour so it stands out. So you've got an angle, two legs, and it's the opposite that you're looking for. So I'll just zoom out so you can sort of see it. So from that kind of descriptive sense, what you're saying is that to work out the that opposite unknown side, the opposite squared is equal to the first leg squared plus the second leg squared minus 2 times the first leg, the second leg, and the cosine of the angle. That's a bit scrappy there, I'll just do that again. Cosine of the angle. I've gone a little bit over there. Okay, that's a very wordy way of saying it, which is why we use algebra, but that's the relationship you're looking for. That opposite is opposite an angle, so that's the match up there. Okay, so the opposite is opposite the angle, and then it's the legs that you sort of use. If you have a look at it, it's really similar to Pythagoras' theorem, isn't it? The square of one side is equal to the sum of the square of the other two sides, and then you've got this minus 2 times leg 1, leg 2 cos angle, which makes up for the fact that it's not a right angle triangle. Effectively, that's what it does. Now, the missing angle looks a little bit like this. So let's just say, sorry, I should explain when you can find the missing angle. If you've got all three sides of a triangle, then you can work out any or all of the angles inside by using the cosine rule as well. Okay? So it is basically a rearrangement of this formula. Ultimately, this formula here is the only one that you really need to understand as long as your algebra is strong enough to do some manipulation. But nevertheless, personally, this is one of the ones that I would probably spend some time trying to memorise as well. And it looks a bit like this. Remember, I'm going to do the algebra in a second. So it looks a bit like this. We've got the cosine of the angle is equal to, okay, we've got the square of the first leg, the square of the second leg, minus the opposite square, all over 2 times leg, whoops, daisy, sorry for that. 2 times leg 1 times leg 2. Okay, so visually, I want you to get an impression of what's going on here. So visually, in your head, it's the two sides that make up the angle that you're doubling at the bottom there. On the top here, you're squaring one of the legs, you're adding the square of the second leg, and then you're subtracting the opposite. Okay? The square of the opposite. By opposite, I mean the one that's opposite the angle that you're either looking for or that you've got, depending on the context. Okay? Get the visual right in your head. Mental model what you're looking for so that you don't get caught up with letters. I'm going to move on to the algebra so that it's the algebra. sorry, Ambrosia, if you find this confusing. What I want to emphasise here is that this is to make a connection between what you need to know and what you in order to solve a problem. It's about, this is the picture. The legs are the bits that make up the angle. The opposite is opposite the side. Okay, so here's the general form here. I'll just zoom out just so you can see it. So c squared equals a squared plus b squared. That's effectively Pythagoras' theorem. Then you've got minus 2ab cos c.
What was the denominator, sorry? Of the
Rule, we just missed it.
Yeah.
2 times leg 1 times leg 2. Okay, thank you.
Yep. It is repeated here as, oh sorry, I forgot the cos, no I didn't, I just stopped up here. Okay, there we go. So, yeah.
Sorry, one question. Why is it written c squared rather than just solve c? Often, because whenever I've seen it written out, it's been written like the first one.
C is equal to the square root of a squared plus b squared minus 2ab cos c. Is that what you meant?
Yeah, but why is it not written with inverse cos, so you can just have c on one side?
I don't know.
It's just convention here.
I guess it's because cos c is standard notation, whereas cos to the minus 1 is just one notation. Other people use a notation called arc cos. So there might be a little, not confusion, but it's a little bit more efficient, I suppose, just to say cos c. And the assumption is that if you're at the point where you're needing to use the cosine rule, you're probably also at the point where it's trivial to work out c if you know that cos c is this. Thank you, good question. There it is a bit bigger for you so you can see it. So what I've deliberately done, you've probably seen it on the second slide there, is that I've said draw the diagram and I haven't drawn it. Because if you've got the visual right, you should be able to draw a triangle and label C, A, B and the big C appropriately on your diagram. We're going to have a go at doing that. So I'm going to zoom out so you can see what I mean. Don't look at slide 7 and slide 8 yet. I want you to look at slide 6 and I want you to draw the triangle which represents the cosine rule. If you're not too sure where the A, B, C and the big C goes, then maybe think about that visual picture again. Which two are the legs? Which one is opposite the angle?
Didn't we just have that?
Sorry?
Didn't we just have that forward through?
Except I used legs and opposites, didn't I? Now I want you to label it with A's, B's and C's.
Oh, okay.
I'll start a timer off. You've got a minute from now. You're looking at slide 5 and copying that down, and then you're doing the instructions on slide 6.
Yeah, but you put a timer on for us to do slide 6. That's not right.
Sucks to be then.
How are you going to do it like that?
Well, what you could do if you're copying down neatly and methodically and you don't have time for it, maybe look at slide 5 and do slide 6 in that minute, and then come back and finish slide 5.
Okay.
30 seconds.
I'll
Just with variables instead of description. Okay, time's up. If you couldn't work out the picture, it means that you haven't got the visual or the mental model yet, and it's worth you having a crack at that. So let me just draw any old triangle. Oh, I should use straight lines. Okay, now just to be controversial, I'm going to label the angle first, and it doesn't matter which one I label. So in this case, I'm going to label the pointy end as C. It doesn't matter which corner, which vertex you label as C. As long as opposite that that angle, you write a little c. It does not matter where you put the little letter A. I'm going to put it down here. You could have had yours on the other leg. It doesn't matter. This one here is the other leg, so I'm going to call it B. So A and B are the legs, C is opposite, and you can see the big C there for the angle C.
Does it matter whether the capitals and the lower cases are angles or sides?
Yes, it absolutely matters that the position of C here is opposite
No.
side C.
So my angles are
Usually
lowercase and my sides are uppercase.
Oh, right. Absolutely, it is entirely conventional to have lowercase for side lengths and capital letters for vertices. When we do things like vector notation and stuff later on, that's going to follow through, so break your habit now. Good question. So technically, if you might have labelled the other vertices, it's a great idea, but you didn't have to. So you've got A and B there. As you can see, the vertex B is opposite the little b side. Vertex A is opposite the little a side. So in some textbooks, don't think ours is one of them. In some textbooks, and ours is one of them, they will actually have three permutations. They will say c squared equals a squared plus b squared minus 2ab plus c. They'll also say that a squared equals b squared plus c squared minus 2bc cos a. And they'll also say b squared equals a squared plus c squared minus 2ac cos b. And then they'll have three more for working out the angle. It's crazy. You don't need, even if the formula sheet has it on it, it's crazy, right? Because as long as you have a good mental model of where the things are in the triangle, you can't go wrong. So again, the mental model is, if I'm trying to find a missing side, let's call it C, but it could be any of these, then I need to know the opposite angle, and I need to know the legs of the other two, the legs that make up that angle. So in that V there, I need these three pieces of information to work out this one. But if this is the thing I need to work out, then I need this little part of the V and the angle in between. If it was A that I was trying to work out, then I need these two legs of the triangle and the angle in between. Okay, so visualize it, mental model, and that means I can't trick you with things like this. I'm just going to skip over to a blank sheet, don't worry, and I will skip back to it. But it means I can't trick you with things like this, and you go, well, I know the rule, it's c squared equals a squared plus b squared minus 2ab sine c. So there's c there, so I'll just go c squared equals 12 squared plus 10 squared minus blah, 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 which gets you this. Because the c is not important. What's important is that's opposite there. Okay? That's what's important. In fact, you can't solve this particular problem with the information I've given you so far. Because if this is what I need, I have no way to work out what that angle is yet. So I can't solve it yet. You can eventually, but you can't solve it yet is all I'm saying, yeah? You can't directly solve it using the cosine rule. Why did I put C?
No, you put. But aren't you, if the big C for the 30 degrees isn't that 10 meant to be side C?
That's what I'm saying, Ambrosia. C, don't be prejudiced, C at the end of the day is just a variable, it's just a letter.
Yeah.
I can, in order to be tricky, confusing, or upsetting, label this unknown side as a C, right? I can just label it as a C, because it's just a variable. But as long as you've got the mental model in your head that this belongs to this, and these are the two legs that these are the two legs that make up that angle. If you remember that, you remember how to plug it into your rule. If you get caught up with saying, well, C is the unknown, so C must go on the left, you'll stuff up every time that they try to trick you. Okay, that's what I was trying to get at the start. The picture is more important than the rule.
And you won't be able to solve it without knowing two legs.
Yeah, if it's a missing side, you have to be able to work out the angle opposite. It'll either be given to you or you'll have enough information to work it out. Yeah? Cool bananas. Okay, so that's drawing the diagram. Now, you know what? I know for many of you, that's really all you need because you've got a formula. You might have come across the cosine rule or not before. But either way, you can just have a crack at it. Basically, using one of those forms of the formula, substituting in what you do know, you can work out the unknown with the equation. It's as easy and as hard as that. So if you have a look here at exercise 11 on page 389, these are the questions which you can now use the next 35 minutes to practice. However, some of you will want to sacrifice practice time so that you can follow on with an example. I genuinely don't mind. I'm going to go through the example now, and if we're videoing it, which means it'll be available on Google Classroom later if you want it. Practice if you want, or follow on with me. Who's going to follow on?
I'm going to do practice.
You going to follow on? Yeah, or just one person. So the rest of you, if you could just keep it to a whisper level, I'd appreciate it. So, can you please quickly, whatever you're doing to get yourself organised, scribble it in the margin or something. Can you please write down the questions? Because I'm about to flick on to the next page. Quickly write them down. Yeah, just scribble them in the margin if that's all you've got time to do. I'll read them out to you. It's exercise 11I on page 389. Yeah, take a photo of the board, it's fine. Question 1, just C or D. Question 2, 3, 5, and 6. Now, I'm going to go through example 14 in the textbook, but I'm going to approach it in a slightly different way from the textbook for good reasons, which I won't go into. Just to reinforce the cosine rule. So example 14 on page 387. So yeah, just whisper level if you don't mind. Gives a triangle with the following properties. First of all, it's labelled A, B, and C. It gives a top angle of 80 degrees. And it gives the two sides, the two legs of that as being 13.2 centimetres and 8.9 centimetres. So that's the label that is given, and what you are asked to do is to find out every side and angle in this triangle. Okay, so I'll be needing to work out this angle, and this side, because I know this angle already. So I'm going to label this side as A because it's opposite big A. Sorry, you'll need to whisper because you're actually putting me off, which is not fair. So I'm going to label it A, but I could label it X, I could label it C if I wanted to be confusing, but I'm labeling it A because it's opposite angle A. So I know that A squared is equal to, now the square of the sum of the two legs, so that means 13.2 squared plus 8.9 squared, and then I subtract 2 multiplied by 13.2 multiplied by 8.9 multiplied by the cosine of the opposite angle, which is 80 degrees. So I can literally just write it in straight away. Now you can see that I did not refer to my formula sheet for that because in my mind I had a strong picture of where each bit was. The next thing is a calculator operation. I will do it on my phone calculator. And I get from that 13 point, oops, that didn't work out well for me. I'll try that again. 13.2 squared plus 8.9 squared minus 2 times 13.2 times 8.9 times by cos of 80, making sure my calculator is in degrees mode, and I get 212.64. 212.65 to round to 2 decimal places. I haven't done it to 3 significant figures yet. Remember, that is not the side length, that is the square of the side length. So I need to square root that in order to work out what that side length is. So I square root it on my calculator, and I get 14.6 to 3 significant figures. Looking at my triangle, does that kind of fit the picture? Kind of does.
Yes.
BC is longer and only just, and it's the longest one. It's not good. It's absolutely worth checking out that it does make sense to your diagram, what you roughly expect. It's just a good little 5-second job that might cause you cause you less heartache later on. The next thing is working out an angle. I've got one, so I'll pick another one. Arbitrarily, I'll choose angle B. And so I'll just start with saying that B is equal to inverse cos of, let me see now, I need the two legs of the triangle. So that means these two things here. Again, I'm just going for the visual rather than the formula. 13.2 squared plus the other leg is the one I just worked out, 14.6 squared, minus the one that's opposite. So that's 8.9 squared. Again, all visual there, right? You can plug it into a formula, just know, I know the picture of the triangle. All over 2 multiplied by 13.2 multiplied by 14.6. And these two things are always the same as these two things, so that's my little match up there. I don't have to stress about it too much. There we go. That's just a big old calculator operation in there. You can do it in one step. I'm going to do it in one step. So for you, you would press the cos, second function cos button on your calculator first, and then another pair of brackets, and then away you would go. I put the inverse cos in last because my calculator works slightly differently. But I'm just talking to the video as well as talking out loud. So I'm putting in 13.2 squared, and then I'm adding 14.6 squared, and I'm subtracting 8.9 squared, and I get 308.19. Now I've got to divide by 2 times 13.2 times 14.6. So to do that on your calculator, just do a whole bunch of divisions. So divide by 2, divide by 13.2, divide by 14.6. Next time I'll use a calculator on my laptop so you can see what I'm doing up on a big screen. And that gets me 0.7995797011. So that's the number I got. I need to work out the inverse cos of that. So if you've done all that on your calculator without starting with inverse cos, you'll have this number. So you'll want to go second function cos, and then go, I think it's alpha button equals for the answer. And that'll bring back the last thing you just calculated. And you should get 36.9. If not, just check your calculations. I'm pretty sure that's right, because I did prepare earlier. Just check your calculations if not. 36.9 degrees would be angle B. So we've still got angle C. I'm going to pause the video for a second and just give anyone who's following on just a minute or two to see if they can work out what angle C is. And stop shouting across the classroom. Okay, which is not going to make sense on that video now. Well done, I think that's about right. So, what's important to do though is that when you've got, when you're solving a problem, it is so easy to stay in the same sort of rules that you've just been using. But I'm telling you now, I'll just for the video's sake, the third angle was calculated by the student by using the cosine rule, and she correctly got, I think it was correct, 63.3 degrees, but we'll confirm that in a second. But it could have been done in under a minute, it could have been done in under 30 seconds. How could that third angle have been solved?
Plus C and A. Oh, yes, find it. Yeah. I'm looking at
C, isn't it, that we're finding?
Oh, they were finding, sorry. Calculate B and A together. Plus them together, just understand. Oh, right, that's it.
Yeah. So that was a deliberate trick.
Yeah.
I think that makes 63.1 by this calculation. So your answer is 63 degrees is pretty much right. It's pretty much right. So the takeaway lesson from this is always step back from a problem and say what's the most efficient way of solving it. So the cosine rule was effectively based on our current tool set. The only way we can solve it is one of those angles. But once you've got two angles in a triangle, using your basic property of a triangle, sum at equal 180 degrees, we can pass that. Absolutely, and that's what you develop as a mathematician. Step back. What's the most efficient way? You need to be more lazy. You can say, I can't be bothered doing this calculation over again. Is there a more efficient way? Even if you spend 15 seconds thinking about it, you'd still be equal about 30 seconds or half an hour, maybe. Multiply that by 10 questions, that's 5 minutes. You just say 5 marks, you try to say. But in terms of calculation complexity, where are you less likely to make a mistake? The way I did it on the board there, or by using the cosine rule again? Yeah, so there's a couple of reasons other than laziness to about the issues. Anyway, that's just a technical side of it. So what have we done? We've got all the that's fine. We've got only one angle. That's impressive. When you look in the textbook, you'll see that they solve the angle column a lot easier too on the sine of basis. I haven't looked at it formally in class yet. So that's what I'm going to do. You happy with that? So just get on with exercise 11I and I'll come over.
Oh my god, I got this right.
Yeah, sorry.
Why are you so surprised? You should be surprised.